Okay, so steps are on page 250 through 251 in your book. Okay, I think I don't want to do the sliding ladder one yet. I want to ease you into this a little bit. So we're going to flip over to number 4. Okay, when you go through and read these, let's underline anything that sounds important. Raise your hand when you hear something that sounds like we should probably underline it because we're probably going to use it. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet. Okay, nothing important yet? From the liftoff point. Are you sure? What should we underline? We have a rangefinder that's 500 feet out. So level field, we know the ground's going to be flat. Okay, at the moment, the rangefinder's elevation angle is that the angle is increasing at the rate of 0.4 radians per minute. So at a specific point in time, which is when the angle becomes, so the angle is changing as it goes up and as following the hot air balloon. At a specific point in time that we get high force, and the angle is increasing at a rate of 0.14 radians per minute at that time. How fast is the balloon rising? Okay, so what's step 1 in our book? Understand the problem. In particular, what does it say? Identify the variable whose rate of change you seek. Okay, that would be in the question. What's the variable we're looking for? It says, how fast is the balloon rising? Velocity. Okay, what are our 2 velocities? Because the velocity is like the measure of some change over. We have 2 categories. Well, like meters per second. What's meters measuring? Distance, or maybe for our balloon, the height over time. Okay, so we want to find dh dt. So, and once you get better at these, when I read the problem, I start writing in my dh dt's and dr dt's and whatever else is I'm looking at. Okay. Change you seek and the variable or variables whose rate of change you know. What do we know? Do we know any rates of change? We're looking at a specific point when the angle is increasing at a rate of. Yep. Okay, but this is not height increasing over time. What's increasing over time? The angle. So maybe what can we call the angle? What do we usually mark in angles? Theta. Yeah. D theta dt. We know d theta dt is 0.14 radians per minute. Okay, step 2, develop a mathematical model. Specifically, a picture helps a lot. We already have the hot air balloon drawn for us. What can we draw with the hot air balloon to show what's going on? We have a balloon rising up from a level field tracked by a range finder that's 500 feet from the liftoff point. I actually rode a hot air balloon this summer for my grandma's 86th birthday. She usually goes whitewater rafting every year for her birthday. Since she was 80, she started going to whitewater rafting every year for her birthday. Her raft is always the raft that flips, so we know not to go in Grandma's raft because it's the senior citizen raft and they always flip. But this year, doctor said, no more. So we went hot air ballooning instead on her birthday. It was really cool. It was really like, I'm a little afraid of heights unless like I'm in control. Like I like rappelling because I'm in control of that. But rock climbing, I don't like that because if I fall, someone else has to catch me. The hot air balloon, you didn't even notice when you lift it off. It's just like, whoop, you just ease up, and it's all smooth. It's beautiful. You should do it one day in your life. No, a little bit of a slightly rough landing, but overall it was pretty nice. Okay, so the hot air balloon doesn't it has a liftoff point, right? That's below it. There's my liftoff point. What else do we have? Rangefinder. Is the rangefinder right below the hot air balloon? No. It's on the ground. How many feet? Rangefinder is on the ground 500 feet out. And when the rangefinder is looking to see how high the balloon is, does it go horizontally to the lift-off point and up to measure? It's going to form a triangle, right? And that's a right triangle. Okay, let's put some things we know about this. We have some numbers. We've added in 500 feet. Anything else that we could add in? Now, I would not write pi force in the angle, because 500 feet, there are some things you have to figure out. What's constant and what is changing. Is the rangefinder from the liftoff point, is that distance constant or changing? This is constant. So we can write the 500 feet on it because it's always constant. Is the angle constant or changing? Changing. So I'm not going to put pi force, I'm going to put theta. I'm also going to give myself like a reminder, an arrow, that it's as the balloon goes up, the theta is increasing upwards. Okay? What else is also changing? Yeah, we have our height here of the balloon. It's not constant because the balloon's going up. So we have to know what's constant and what is changing. This actually makes sense because from our what, we're looking at dh dt. So that will be changing, and d theta dt. We have theta. Okay? So we have our picture. So this was step 1, your wants and knows. Step 2, draw a picture. Step 3. What does step 3 say? Jake, can you read step 3 there? Okay, or in shorthand, we need a formula involving these two, theta and height. Okay, looking at our picture, what type of formulas have you learned in all your years of math that would involve a theta and a height with this right triangle? Trig, right triangle trig. Okay, based off of where our theta is, here's theta again. What's h's relationship to theta? Opposite. And we know the base, 500 feet. What's 500 feet's relationship to theta? Adjacent. So think of trig, so katoa. Which one involves opposite and adjacent? Tangent. Exactly. So we'll be writing our formula involving tangent. Tangent of theta, because we don't know theta. You do not plug in pi force until the end. Okay, tangent theta equals, because pi force is changing, so we're not plugging it in yet, equals opposite, let's see, TOA, opposite over adjacent. So that'd be h over 500. We can put 500 because that's a constant. Okay. Okay, and we're going to solve because of what we want. We don't want d theta dt. We already know d theta dt. We want dh dt. So this guy we're going to solve for h, because that's what we want. And then we can take the derivative and find dh dt. So h, isn't that just 500 tangent theta? Okay. Okay, step 4, I've already told you, and you can read it there in your book. Differentiate both sides implicitly with respect to time. Okay, this is where you have to be careful on how you differentiate. Differentiate implicitly with respect to time. Okay, so if I'm going to differentiate, oops, red doesn't look so skinny. Okay, maybe. I don't know what's wrong with this. Skinny. Okay. I'm going to write my tangent theta, and I'm going to show that I'm going to take the derivative with respect to time. So in front of it, you write d dt. Oops, 500, excuse me. 500 tangent theta. Remember, you have to have something after that tangent. Don't just write tangent. And I'm going to show that I'm going to take the derivative of h. But it's with respect to time. So when we're taking the derivative with implicit differentiation, if you're taking the derivative of a theta with respect to t, you have to remember d theta dt. If you're taking the derivative of h with respect to t, you have to remember dh dt. Okay, if the variable you're taking the derivative of doesn't match your respect, then you have to have dh dt or d theta dt, okay? So, derivatives of tangent. What's our little reminder of how to find derivatives of secants and tangents? I saw this on some of your tests, which is awesome. So tangent then is secant squared. Okay, so we have 500 is just a constant. It's not going to change. It would be secant squared, what? Theta. Good, d theta dt, because we are taking derivative with respect to t, and since theta is not t, we have to write d theta dt. And the derivative of h with respect to t is 1, dh dt. Okay, so that was step 4. Step 5, now we can substitute. You do not substitute in the changing pieces until after you've taken the derivative. Okay, 500 is a number. Secant squared theta. Do we know theta? Yeah, pi 4. So we're finding the how fast the balloon is moving when the theta has reached pi 4. So now we can plug it in. Pi 4 equals dh dt. And that's what we wanted. dh dt is already isolated. So we're not using a calculator. We can do secant of pi 4 and then square it by hand. How do we find secant of pi 4 if you don't have it memorized, which I don't have it memorized? Secant's the reciprocal of something. So if you don't know, I write myself a little reminder. The order goes like this. Tangent, I know, the reciprocal is cotangent. And it goes CSC. Okay, so these two are reciprocals. So if I know cosine of pi 4, then I can find secant of pi 4. So I draw a little. The pi 4 should be easy ones to memorize, but if you don't know, you draw yourself a first quadrant. Everything's over 2. Remember the pattern? 1, root 2, root 3, 1, root 2, root 3. Which one's cosine, the first or the second? first. So in this case, it doesn't matter, right? Because it's the same. Okay, root 2 over 2 is cosine pi fourths. So if we want secant pi fourths, we have to flip it, which is 2 over root 2, but we don't leave it with the root 2 in the denominator. We have to rationalize the denominator. How do you remember how to rationalize the denominator? Well, it doesn't really have a conjugate in this case. Yeah, square root 2 over square root 2, which gives me 2 root 2 over 2, because root 2 times root 2 is 2. And we get a nice, pretty root 2, which actually goes out really nicely in this problem because it's secant squared. So 500 times root 2 squared equals dh dt. And I'll give you a second to catch up. I'm just trying to simplify. Okay, and root 2 squared is 2. So we have 500 times 2 equals dh dt. So we get 1,000 equals dh dt. Oh! I missed something that we needed to times by. Look! d theta dt. I was like, I don't remember it being 1,000. We didn't plug in one thing. What is d theta dt? 0.14. So after the pi fourths, we have to times by 0.14, which is really not too bad to times by 1,000. Times by 0.14. If you times by 1,000, doesn't that just move the decimal 3 places because there's 3 zeros? So if I take 0.14, move 1, 2, 3, I get 140 dh dt. What would the units be on this? Height over time, what are the units? Yeah, I believe this is in feet. Yep, feet per second. Okay. Well, let's see what. Yep, radians per minute. So you're right. Okay, so when theta reaches pi fourths, the height is increasing at 140 feet per minute. Okay. Okay, now we're going to do number 1. Now that you've had an introduction. We're going to do probably at least 3. I might have you try one on your own. And they're all different. So you have to take all your wealth of knowledge of formulas that you've ever learned to be able to, and draw the picture to be able to deduce how to do these. Okay. So, underline anything you see that's important. If you already realize it's a rate, try to in the problem write like dh dt or d theta dt. Find the unit of over time. If you know it's a rate, I would write that in the problem. A ladder 20 feet long leans. Is that something important? A ladder 20 feet tall leans against the wall of a vertical building. This is a sliding ladder problem. If the bottom of the ladder slides away from the building horizontally at a rate of 2 feet per second, okay, how fast is the ladder sliding down the building? How fast is the ladder? We need to know which direction we're talking about. Down the building. when the top of the ladder is 12 feet above the ground. In this case, I think it might be easier to draw the picture before you do your knows and wants. Okay? So for the drawing, we have a vertical building. Yeah, I'll just leave it open. And we have a ladder leaning against it, right? Which creates a right triangle. Do we have any information we can plug into this? Is that a constant? Yeah, now this is something that apparently people forget, that the ladder, when it's sliding down, the ladder's length never changes. It's always 20 feet. So I would even write a note to myself that that is a constant. Okay, let's see. And the ladder slides away. So if I draw some arrows showing motion, it's going to be going this way, right? So the bottom is increasing. What's happening to the height against the wall? The height is decreasing. Okay, so we have two rates of change there. What could we call this rate of change here? Oh, it's the x-axis. Yeah? So could we call it dx, dt, the change of the x with respect to time? So our 2 feet per second is dx dt, because it's going horizontally. Horizontal axis is dx dt. Okay, so if this was our x, this is our y, so its rate would be, we could call it dy dt. And I think that's what we're trying to find, yeah. How fast is the ladder sliding down? We're trying to find dy dt. Okay, so we can fill in our know. We know a few things. We know the ladder is 20 feet. Can we give a name for the side of the right triangle? Hypotenuse, what do you want to call it? H, sure. So I would label it equals H for the hypotenuse. H equals 20 feet. We also know horizontal rate of change, which is dx dt, equals 2 feet per second. Do we know anything else? Okay, that's a good point. Not getting mixed up with height. Or we could just give it a different letter completely, because we're going to have this in a formula, and I want to be writing HYPs all over the place. How about we give it C? Okay, what are we wanting to find? Because we've written everything we know. What are we wanting to find? dy dt. How fast the ladder is sliding down? Down will be the y-axis. dy dt. Okay, so even though we're going to do these in reverse order, so we have the first two steps. The third step is to determine what type of formula you're looking for. Okay, we need a formula in terms of our two rates of change. We have an x and a y. What type of formula involves a right triangle where we're looking at the legs, the lengths of the legs? What? Pythagorean theorem. Even though we didn't label A, B, and C, The a and the b are your x and your y. So in our case, it would be x squared plus y squared equals that hypotenuse, which we conveniently changed it to c squared. Okay. What do we do now? What did we do in the last problem? Not yet. We're still on step 3. We need to get it into terms of the variable we want. We want only y's. But we have x's and y's. We know c is a constant, so that's going to be okay. We have x's and y's. How can we get into terms of only y's? Exactly. Yep. So we know it's okay to plug in the constant early, but you can't be plugging in the changeables, like the rate of changes early. So we know y squared equals 20. I'm going to solve it for x and then plug it in, so then everything is in terms of y. Okay. And if you can do the 20 if you want, or you can do a c squared. But in case you forgot c squared as a constant, I'm just going to put c squared, and we'll talk about this in just a minute. So x squared equals c squared minus y squared, square root it. So you get c squared minus y squared, all underneath the square root. So if we replace x, remember it's squared, with square root c squared minus y squared plus y squared equals c squared, then everything's in terms of y, and we know c is a constant number 20. So it's okay now. Step 4 would be take the derivative, implicitly differentiate. Now, if you don't plug in the 20 right now, you have to remember this is a constant. What happens when you take the derivative of a constant? Equals 0. Okay, so if it helps you, you can put in the 20, but that's only because that's constant. Don't plug anything else in. Root, oh, and this is all squared. Did you all put a squared after the parenthesis? 20 squared is 400 minus y squared plus, and actually if we square the square root goes away, right? So, whoops, that's not. So I'm just going to write 400 minus y squared plus y equals 20. Plug it in the square, which is 400. Take the derivative, step 4. Something's happened. Why are all my y's going away? What? Yeah, that's supposed to be okay. Oh! I'm not supposed to plug in the x until after I differentiate. That's the issue. Okay. Sorry. Don't plug in that x until after we differentiate. Okay, so step 4, implicitly differentiate. So we get, but we're doing it with respect to time. So if you need to write out at the beginning, I'm going to take all of this with respect to time, take the derivative with respect to time, and you can see that the letter doesn't match. So you're going to have dx dt's, you're going to have dy dt's, you're going to have dc dt's. So it says derivative with respect to time of x squared plus y squared equals derivative with respect to time of c squared. So we get 2x, but since x wasn't time, what do we have to have after the x? Dx dt plus do y, what comes after the y? dy dt. Equals, now we've already talked about this one, this is a constant. When we take the derivative of a constant, we get 0. And if you plug in 0 right there, makes your life easier. Now we can replace our x with this guy, so we're all in terms of one variable. Two times x was root c squared minus y squared dx dt plus 2y dy dt equals 0. Okay. Let's solve for what we want, and then we just plug in. Okay, what are we looking for? Dy dt. So all of this good stuff needs to be subtracted over. And actually, because the right-hand side is 0, we can simplify. Do you see anything that cancels out because the right-hand side is 0? Or it would cancel later. It's up to you. Don't they have a common factor? 2. If I divide out a 2, it goes away because 0 divided by 2. Otherwise, when you're moving things around, eventually it would divide out anyway. But if you see it right now, you can just cancel those out. And then subtract root c squared minus y squared, both sides. Subtract root c squared minus y squared. Those cancel. Oops, and we need to, let's subtract the dx dt at the same time. We can deal with those all in one step. You get y dy dt equals 0, which we don't need to write, minus c squared minus y squared dx dt. Now, if you're running out of room, a nice pretty arrow showing where you're going would be nice. Divide out the y, so we get dy dt equals negative root c squared minus y squared all over y dx dt. And this time I won't forget to times by dx dt. Okay, so now we can plug in things we know. We're looking for dy dt, so we don't know that. Minus, what is c? The hypotenuse of 20. And 20 squared is 400. Minus y. Do we know y? We know why. Yeah, Alex, say it louder. 12 feet. There's actually one more thing we knew. Y equals 12 feet above. Right there. No, we are finding how fast the ladder is sliding down when the ladder is 12 feet above. When this point is 12 feet, we're looking at how fast it's sliding at that point, 12 feet. Okay, so we actually do know y. 144, because 12 squared is 144. Divided by 12, and don't forget, we're not going to forget it this time, dx dt. I believe they gave that to us. 2 feet per second. Now, feet per second, what's the unit on this numerator here? 400 was representing a 20, the length of the ladder. 144 is 12. What's the unit for both of those? Feet. Just to make sure the units would work out. Just to make sure. Not being skinny. And 12 is also feet. So do we actually get feet per second? Yeah, because those feet cancel out. So we have negative root 400 minus 144. 2 256, is that right? And over 6, because 12 divided by 2 is 6 feet per second. This one doesn't come out nicely. So if it's one that you're allowed a calculator, you could then type it in and get 4 decimal places, right? Don't chunk it off too early. Otherwise, your other option could be to just simplify the square root, but that's about as far as you can go. Does square root 256 break down? Guys, 256, it's even. What's half of 256? 128 divided by 4, 12 divided by 4 is 3, 8 divided by 4 is 2, 2, 2, again 8 times 4, 8 has 3 2's. Wow, that's a lot of 2's. How many 2's in total do we end up getting? 8. Actually, maybe 256 is a perfect square. Is it? I think all of them are going to pull out. Yeah, because there's 1 group, 2 groups, 3 groups, 4 groups. 2 to the 4th power. 2 times 2 is 4. Is it 16? Ah, that does come out nicely. So we have negative 16 over 6, which is negative 8/3 feet per second. Okay, do you want to try one? I'm going to give you the starting of this next one and then let you go. Because the starting, it's different. Like I said, all these problems are different. How about let's do this first. Stand up, because these are kind of tedious. Stand up. If you need a drink, hurry and go get a drink, but be quiet in the halls, please. And come back, and then I'll start you off on the problem and then let you try the rest of it. Okay, let's start you off with number 5. Yep. So we've done a sliding ladder. We've done hot air balloon rising. Now we're having something coming in. Water going into a cone. That's good stuff. Okay, but I'm definitely going to start you out because, yeah, there's a long way to do it and a short way to do it. If you realize the short way, your life will be easier. Okay, water runs into a conical tank at the rate.
Teacher, so sorry for the interruption. If you have students who are signed up for the engineering field trip, would you please let them come to the Career Center? Students, you should have received this book if you're...
None of you are going on an engineering field trip? You're all of our calculus students. I didn't know about it either. Is it this one? No, that's February 20th. That's true. Okay. I see the word rate, and I see a rate, 9 cubic feet per minute. Cubic feet per minute. We have a cone. Cubic feet per minute. Can we write a rate in the problem? What's our unit? Volume. Cubic feet per minute. So what can we say this is? Volume prime, okay. How do we write that with the related rates though? dV dt. So now that you've seen a few of these, when you start reading them, you can mark it as you read it. dV dt, because we're talking about volume. The tank stands points down and has a height of 10 feet. That's probably important. And a base radius of 5 feet, even though the base radius is at the top because it's pointed down. How fast is the water level rising? That's a rate, isn't it? With respect to time. What with respect to time? If it's rising, height. So dH dt. okay? When the water is 6 feet deep, okay? Luckily, they've already given us a picture. Let's fill in some things we know. What can we put on the picture? Okay, and that would be the outsides, right? So the height of the cone is 10 feet. So this long arrow right here is 10 feet. Does the height of the cone change? No. So this is a constant. You have to determine what's changing and what's constant. Okay, what else can we put on? Okay, I heard radius. We know 5. Is it this radius? Or is it this radius? Yeah. 5 feet for the radius. Is that radius changing? No, because it's the container. That's also constant. Bless you. What? Yeah. Okay. Anything else? The height of the water. Now, that's what we're going to find here in a sec, is when how fast the water's rising, when it's 6 feet deep. So, what would we call this right here? The height of the water. And is the water going up or down? It's going up, so I'm going to give it motion up. That will be our dH dt. What else is also changing? The radius of the filled water. So our radius is expanding, right? As we fill in water, the top radius gets larger and larger and larger. dr dt. So we have 2 constants and 2 that are changing. Okay, so things we know. We know 6 feet deep is what? 6 feet deep. dH dt is what we want to find. 6 feet deep will be our R, but we have 2 R's, so we might need to specify. This is like R1, and this is R2. Because we'll want to know when it's 6 feet deep. Oh, not R. Height. We have 2 heights, sorry. Okay. So we have 2 heights. We have our original height, and we have the height that's changing. So h sub 2 will be 6 feet deep. We also know dV dt, we already marked it. What's the rate of the volume changing with respect to time?
Well, how do you know the volume is the radius of the water?
Volume can't be the radius of the... This is an R. This is an R.
Like arrow looks like the radius, is that not?
No, it's just saying which way it's increasing. This arrow says that my height is going up. This arrow is just saying that... This arrow? Sorry.
No, it's not what you did, it's how the picture is drawn. Because the arrow looks like it goes from the middle of the cone to the edge of where the water is. So it looks like a second radius.
Because there is a second radius. That is the radius of the top of the water, which is a circle. It's not a volume. It's an R. It's an R. The R dt. We haven't written 9 on here. That's a V. The volume is changing with respect to time at 9 cubic feet per second.
So we have an R dt down here and not up here.
Because this right here is just on the radius. Because the volume involves a radius and a height, right? So we have dr dt, and we have the height dt. Yeah. Yep, we have our dr dt and our dH dt. And we're given the volume, dV dt, is 9 feet cubed per minute. And we also, it's not on the picture, nope. Okay. We also know the tank stands. We know the height. H1 is 10 feet. We know R1, the original, is 5 feet. We know a lot. We want to know what? DHCT. We want to know DHCT when the water is 6 feet deep. Okay? So, those are the first two steps. Step 3 is we need a formula that's in, with respect to what two categories? We need a formula involving what? Okay, so just take the tops, V and H, so volume and height, right? Volume and height of the cone. Do we have something like that? Yeah, we do. 1/3 pi r squared times H. Now here's where you have to be careful. Okay, we know R, right? The original radius is 5. But are we given dr dt? No. And we're not looking for it either. We're looking for dH dt. So that's an extra thing to solve for. What you can do is just really involved. Or you can use your knowledge of similar triangles and make your life a little easier. So if we don't know dr dt and we also don't know dH dt, so that causes a problem. But we have similar triangles because they're right triangles. Okay, so we have our radius and what are our categories? Radius and height. So we can make a ratio, because of similarity, make a ratio of radius to height. The radius divided by the height of each triangle should be proportional. The radius we know of the cone itself, and we also know the height of the cone itself. The radius is 5, and the height was 10. Now remember, we want to get this all in terms of what we're searching for. We're searching for height. So we're going to solve this one for H. Or, excuse me, solve it for R so that we can plug it in for R, and then everything's in terms of height. So if we solve for R, we get R equals 5 divided by 10 simplifies, right? To 1/2 times by the height. We get H over 2. Okay. Oh, get it right, a little smaller. So my volume is 1/3 pi, but now the radius squared is H over 2 squared times the height. That's where I'm going to leave you. Okay? You know what you need to do now? You're trying to find dH dt. So what do you have to do? Take the derivative. After that's done, then plug in stuff you know. Okay? I'll let you finish. Work with your neighbor if you need to.
What I can't use is we're solving for at the point 6 water 6 feet.
You don't plug in anything that's changeable until the very end, because it's not a constant.
Right.
Because it's rising, that depth is always changing. All right, I'm going to go over it, just check how you did. And looks like I have to write a little bit smaller. Running out of room. Okay, so we left where we came up with a formula and we got everything on the right side with h's only. Okay, now we're to the point we have to take the derivative with respect to time. So I'm going to write the formula again, but I'm going to take the derivative with respect to time. That's what d dt means, is this is saying my next step will show the derivative of v, and I take the derivative with respect to time of all of that good stuff, but I'm going to simplify a little bit. 1/3 and pi are constants. H squared and 2 squared. We have to square both of them, so we get h squared over 4 times h, right? So don't start changing things on that line. Go to the next line. If you're going to combine those, don't combine them on that line. Go to the next line and rewrite it. 1/3 pi h cubed over 4. Now, as long as it's right, that's okay. Okay, now, if you look at this, everything I'm circling in red is a constant. Okay, everything circled in red, nice little pretty arrow, so I know I'm going to the left. Everything in red is a constant. So I can pop everything out front, because sometimes it's easier to see that it's a power rule if you have your constants separated from your variables. Okay, now if we do the power rule, I get dv dt equals power rule. I bring down my 3, and it will cancel out. You can change that to a 4 if you want, but or to 12 if you want. You'll just have to simplify. Decrease the exponent on the h to 2. My 3's cancel. I have dv dt, times dh dt, right? Because I took the derivative of h with respect to time. Equals pi fourths is a constant. H squared times dh dt. Any questions up to that point? Okay, we are looking for dh dt. So I'm going to replace dv dt. I should know that. What's dv dt? dv dt is 9. Pi fourths is a constant. We should know our h at this point in time. We're looking for when the height of the water is 6. And the only thing we don't know is dh dt. So everything should replace to a constant. And you simplify. We get 9 equals 36 pi fourths. There's different ways to simplify this. I'm just going to simplify before I move it over. 36 divided by 4 is 9. So 9 equals 9 pi over, yeah, I don't need the over. 9 pi dh dt. Now when I divide by 9 pi, what was that? I get 1 over pi dh dt. What's the units? Feet per, minute. Now, if it was a calculator section, then you could type it in and get the actual decimal, and you chunk it to 4 decimal places. But a couple of you were getting decimals too early on. This is the equivalent answer to the decimal, isn't it? Just leave it. Unless directions specifically say what is the decimal out to like this place value. Leave that. Because it's an equivalent answer. Put units though, because it's a story problem. So your homework is not from the book. I have a worksheet of problems called True for Related Rates. Some little fun things. There's a couple cartoons. Do you want me to hole punch these? Okay, I'll hole punch. So due next time, we have the WUTC, the optimization, your extra implicit differentiation assignments, and questions on Turvy for related rates. There we go. My friend did these for me. I went to a military ball on Saturday, so my friend did them. And now I'm like, I really like them. I want like the equipment to do it myself now. Have a great weekend too. I know, actually, fourth period yesterday, I thought it was Friday, and I was like, oh wait, calculus is tomorrow. I should probably prepare that lesson. Huh.
I didn't do any remedial homework until late last night. I was like, luckily I had most of it done. I was like, oh, I have the weekend.